Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. The topic of this video is elementary matrix operations. Elementary row operations and elementary column operations depend on the context and the specific problem to be solved. Both types of operations can be used for matrix manipulations, but they serve different purposes and are used in different scenarios. Elementary row operations are preferred in most contexts, especially when solving systems of linear equations with Gauss elimination method, finding the determinant, or inverse of a matrix with Gauss-Jordan method. Elementary column operations are less intuitive and not as commonly encountered in standard linear algebra problems, especially when solving systems of equations. Elementary operations are in principle applied to augmented matrices. Upon employing row or column operations, also referred to as row or column reduction, an augmented matrix is transformed into an equivalent matrix. A word of caution: when a matrix A is reduced to another matrix, say B, by a series of row or column reductions, matrix A is said to be row or column equivalent to B, and is denoted by A equivalent B notation. Here it is incorrect to use an equal or right arrow sign instead of the equivalent symbol for equivalent matrices. Elementary row operations are applied in linear algebra and matrix theory for several reasons. To solve systems of linear equations efficiently. To find the inverse of a matrix. To determine the rank of a matrix. To simplify matrices and make further operations easier, such as determinants, eigenvalues, etc. To analyze linear dependence independence and spaces, row or column spaces. To determine the consistency and uniqueness of a system solution. Row reduction is the process of transforming a matrix into a simpler form using elementary row operations, which is applied to solve systems of linear equations, or find the inverse of matrices, or compute the matrix rank and determinant. The goal of row reduction is typically to convert the matrix into row echelon form or reduced row echelon form. Consider a 3x2 matrix, which has 3 rows represented by R1, R2, and R3. It has 2 columns, which are denoted by C1 and C2. We use these notations to describe row or column operations. Consider the following 3 equations with 2 unknowns, x and y. The augmented matrix is formed as follows. In large augmented matrices, you may use a vertical dashed line to separate 2 matrices. The given system of equations has a common solution of 4 and -3, and in the following examples, we will be using this augmented matrix to illustrate the row operations. There are 3 types of operations: scaling, pivoting, and elimination. The scaling operation involves multiplication of a row or column with a real scalar number. A row, or a column, of an augmented matrix can be multiplied by a real non-zero lambda to obtain another row, or column. Note the notation for row operation. The results are overwritten on the row the arrow points to. To understand what scaling does, consider the system of linear equations and the augmented matrix as shown. Each row operation is indicated with an arrow pointing to the row it is applied to. According to this coding, The first row elements are multiplied by 3, the second row by -2, and the third row by 4. Notice that, given with an equivalent symbol, the augmented matrix rows are modified accordingly. The scaling means that every equation of the system is multiplied with a scalar as shown in the equation form. The coefficients of the equations in the system are altered, but this process does not affect the solution of the system of equations. The pivoting operation is simply the interchanging or swapping of rows or columns during row reduction. This is done to ensure that numerical stability is maintained and that row operations proceed efficiently. In this context, pivoting refers to selecting a pivot element in a matrix to use as the leading entry in a row, then performing row operations to simplify the matrix. Any two rows or columns can be swapped to achieve pivoting. Pay attention to the notations used. The goal is to make the matrix easier to solve, typically by transforming it into row echelon form or reduced row echelon form through Gaussian elimination or Gauss-Jordan elimination. For example, in the following augmented matrix, if row 3 and row 2 are to be interchanged, this elementary operation is coded with a bidirectional arrow as shown. The corresponding row swapping operation is illustrated on the augmented matrix. In equation form, this pivoting operation results in simply changing the order of two equations, which does not affect the solution of the system of equations. The elimination process in row reduction is a key step in transforming a matrix into a simpler form, such as row echelon form, or reduced row echelon form. The primary goal of this process is to systematically eliminate variables by using a linear combination of two rows. We use the linear combination of two rows, or columns, to eliminate elements by creating zeros below, or below and above, the pivots in each column. Here, using real values of m and n, the linear combination of ith and jth rows, or columns, are computed and overwritten on row k. Consider the following augmented matrix. Suppose we want to create a 0 in the third row of the first column. We can accomplish this by multiplying the first row by -2 and adding it to row 3. The operation is illustrated as shown. Performing the coded row operations creates a 0 at the desired location. In the meantime, it modifies the third row elements. In equation form, this corresponds to multiplying equation 1 with -2 and adding it to equation 3. This leads to, or summing them gives 3y equals -9. Row reductions on an augmented matrix allows us to easily carry out such tasks. Advantages of row operations. Row operations are easier to understand and simpler to apply. Row operations are directly related to solving systems of equations, a focus in linear algebra. Row operations preserve the solution set of a system of equations when used correctly. Be careful in applying row operations when computing determinants because scaling and pivoting do change the determinant. Column operations are less intuitive and not as commonly encountered in standard linear algebra problems. Column operations can change the properties of the matrix in ways that are harder to track compared to row operations. Column operations are generally not as directly applicable to standard algorithms for solving systems or finding inverses. That is why the majority of computer codes make use of row operations. That is all for now. See you next time with another topic. Bye.